Hello, this is a follow-up note, video note on plotting the Symmedian point of a triangle, which is the most likely position, assuming all three sides have the same accuracy. I did a short video the other day using just a random triangle drawn on paper, but now we want to work towards applying this to real data. And here's some sites from an actual voyage of. I've got 2 or 3 voyages that we've saved all the details of from the early 80s. I mean, that's I guess the last time you were forced to do it that way. And so we've got that data. And so here, I'll do one example, but here's the point. Let me see. These are some actual plotting sheets, which I've then covered with some plastic to protect them over the years. But this is like sorry, a little bit messy, but it's more organized in the logbook. But here's the DR track, and then here's a fix, and like here was a DR, and then this fix bounced us up this far up here. Then we carry on with the DR track and do something. I'm not sure what happened here. But then here's the point. In just sort of the routine work, we're using this scale here, 25 to 26. That's degrees, so that's 60 miles. 60 miles. So it's hard to get a very accurate fix here like that with this scale. So when we really care about it, then we expand the plot to its... now we have what, 39 plus 6. Yeah, so this is now 6 minutes. So this is now 6 miles. 6 miles, not 60. And each one of these lines is not just one line. It's actually multiple sites of each of the bodies, which are then corrected for the motion of the boat for each site. And then we use our fit slope method to find the best line of that series. So each of these represents some amount of correction. See advanced. Okay, somewhere, okay, so this may be without, it looks like, I just saw a note here, it looks like this one is not yet done. It's a preliminary plot without having advanced each of the lines to the same account for the motion of the boat. But that doesn't affect what we're doing. So here's a real scale. So what is this? This is 1, 2, 3, 4, 5, 6 miles. So what is the size we're talking here? This is like... like 3 miles around here. So, and apparently at the time this was done, I chose a position here. Now, whether or not that was the best or not, it doesn't matter. That's not the point here. We want to now say what is ideally, theoretically, the best point, assuming all 3 of the lines are the same precision. And that's the whole thing we're going to work up to. The lines are rarely the same precision, in large part because of the quality of the horizon. When the sun goes down, in the direction the sun's going down, the opposite direction has a darker horizon, and so forth. Or there may be some haze somewhere or something. But okay, and then the other way, I'm just going to try to see if I can. Yeah. So let's see. Does that show? Yeah. So I'm just going to do that and mark these corners here, and like that, and then do it on this piece of paper, and then I have to label them. Well, we have to measure them in length. And now this, we know what this is. This is the real scale here. But when you do this analysis, it doesn't matter at all what the scale is, right? We know what this scale is. This distance from here to here is about 2 miles. Really, that's about, they're all about, this may be a little bit longer, but these are about, this is a cocked hat, and the sides are 2.5 miles long. But that doesn't matter. Here we use any units we want. We're going to use, what are these? These are, we're going to use tick marks on a 1 to 80,000 chart scale. But that doesn't matter. So, but first we have to label them. I'm going to do A, B, C. And our system requires we go clockwise. And then we can just start doing these. And then I can measure this from here to here. What do we get? Oh, that's exactly That's 10, 11, 12, 13. So this one is 13. That would be C. So C equals 13. That's the side opposite the angle C. And then this one would be B. This one would be B. And that would be, oh, look, that looks like it's exactly 10, 15, 16. I'm going to call that one 16. And that would be side opposite that. That's B equals 16. And then A, the other side of the triangle, would be from here to there. That looks like a little bit hair over, but let's call it 13, 10, 11, 12, 13. Yeah, let's call it 13. Looks technically to be, well, actually, these things aren't going to matter that much, but that would be more like 13.2. But let me just see that again here. Oh, now when I put this up there, okay, I'm going to have to call that 13.5. Okay, 13.5. A is equal to 13.5. So now we bring up our tool. Oh, the other thing I have to do is see where we actually chose the point. And here is this app. And so can you see that? Okay, I'll get over here where you can see it. Okay, so side A, that's why we label these, because we're going to measure a distance. Like this is A. I'm going to think of some point up here called A prime, A prime. And I'm going to, this little app is going to calculate B to A prime, C to B prime, like that. So, and it just keeps it in order. So what do we want? Side A is 13.5. 13.5, yes. Side B is 16. 16.0, it doesn't matter, 0.0. Side C is 13.0. I'll just do that for completeness, for symmetry. Okay, well, it's already calculated the point we want, the stuff we want. And so, I don't know if I moved this out of your view, sorry. Now, but these are the things that's counted. B to A prime is 5.4, 5.4, 5.4, B to A prime, B to A prime. So we want here something 5.4, and then we've got C to B prime is 8.3, 8.3, and then A to C prime, 7.6. That's 7.6. Okay. Now I have to draw those in. So A to C prime, this is 5.4. And see, I'm doing this on like a real chart scale here. 5.4. That's 5. That's 5. That's 6. 5.4, something like right there. And then, so this line then goes from here. Oh, I've got a lot of, it's interesting. There's a lot of padding somehow underneath there, so the drawing not that accurate. Okay, and now this is now C to B prime is 8.3. So that's, let's see, that's 8. 5, 6, 7, 8. 8.3 would be, something like that. And so there is, this line goes from here to there. Now let's do, in principle, that's the answer, but it's always check to see we didn't make arithmetic or something mistakes. So we got A to B prime. No, what? No, A to C prime, 7.6. Okay, so that's 7.6 is going to be about, 7.6 is about here. And then this line goes from here to here. Oh, it looks like it's about right, even. Okay, so that's the Symmedian point based on those sides. Now, actually, where did I actually... Now, it doesn't matter where I really chose it, but... oh, look at that. Well, it's essential. When you get a triangle that's like this, almost equilateral, then the G, the center of gravity, or the centroid of the triangle and the Symmedian of the triangle are essentially the same. They're on top of each other when you have an equilateral triangle, and when they're isosceles triangle, they two sides the same, then it's going to be one on top of each other like that. And so that's not a surprise. In this case, I had no thoughts in those days about the Symmedian business. I just took the centroid, and so that's what that is. But this is not so much that. And now I have to go back, and we've got them, right? This was a real ocean voyage, so we got sites with all kinds of shapes and whatever. So I'm going to find one where, hopefully one where there's a little more uncertainty even than this, and then skewed, where the triangle is not just equilateral or isosceles. But the procedure, what I want to do is show the procedure, and that the procedure is realistic numbers you can measure with real tools here. I was talking about, getting out micrometers. That may be a faster way to do it, but that's not a normal tool in the nav station. So anyway, that's the way that you would plot the Symmedian point if you were someplace where you really cared to do the very best.